In this tutorial we're going to look at making sense of MANOVA. MANOVA is a generalization from ANOVA, where instead of increasing the number of IVs as we did in some of the previous tutorials, you increase the number of DVs. This makes sense when you've got something which is complex or difficult to make sense of by looking at one small aspect of it, and you want to look at it as a whole where you've got multiple correlated outcome variables. So one of the places where this might be true is if you're looking at something like self-efficacy. We know that self-efficacy is talked about in the literature in terms of multiple domains, things like academic self-efficacy, sporting self-efficacy, social self-efficacy. So let's say we're doing a study and we want to see if self-efficacy is differing in terms of general self-efficacy and academic self-efficacy in a particular group. So in this case we're going to look at sex differences. So you can see in the exercise we've got a little story here. Researcher believes that while academic self-efficacy is related to general self-efficacy, people's experiences may contribute to the development of several subdomains that are to a degree independent. Moreover, the researcher believes there may be sex differences in domains where gender stereotypes favour one gender. Put it that another way, males and females might differ in terms of their self-efficacy, particularly say in terms of academic self-efficacy. To investigate this issue, the researcher has obtained a measure of general self-efficacy and a measure of academic self-efficacy for a group of 139 first-year university students. So we've already got that in a data set, and we're going to have a look at that in a moment. As prior research informs her that sex differences exist in general self-efficacy, she hypothesizes that males will score significantly higher than females on the general measure, but she believes that a favorable gender stereotype for female academic success may influence the scores on academic self-efficacy, resulting in little if any gender differences on that domain. Okay, so we're going to look at this by first of all opening up SPSS. I'll go to this one here and show you how we would do it, assuming that we have a file already created. In this case we go up to the File menu, we go File, Open. We select Data because the data is already in an SPSS data file, and it's in a directory called Psych 71409. You can find this on the S directory. So if you were to go to your computer, okay, you can see here courses on data 2, and you can find a directory psych data 409, and the file we want is called sexdifferences.sav. So we'll grab that, go open. Open a new window in this case. I've already got it open because I was having a look at this earlier. Now you can see here again we have data set up in the format that should be familiar by now. We have each line of data represents one person. So this is a row. And each column of data represents a variable. Okay, so the first column represents the participant being tested. Participant 1, participant 2, participant 3, it must be between subjects design. We have the year of study, this is in school, so this is year 7 in school. Their age, 13. Their gender, 1 and 2. 1 and 2 is actually a poor coding strategy for this. I want to get people into the habit of using dummy coding. So what we might do is recode that into 1 and 0. The other thing is at the moment we can't see what they are. There's no labels put on this to say which one's males and which one's females. Okay, so I'm guessing that this is sex, I'm guessing it's 1 or 2. What can we do to actually make more sense of that data? Well, we can do a frequency distribution, because we know in most university populations or in school populations you get more female respondents than male respondents. So we can look for females as the most abundant group and apply a label according to that. Of course, if you're doing this for real, what you'd be doing would be coding the data and labeling it appropriately at the beginning so you don't get yourself stuck in this position. And then at the end we have 2 dependent variables. Normally we would analyze one of these dependent variables at a time in an ANOVA, but in this exercise what we're going to do is create a single test that uses both of these simultaneously. This is called a weighted linear composite. Okay, the weighted linear composite is a combination of these two things giving you one overall virtual score which is being analysed. Okay, so before we do that, let's just quickly have a look at this X variable, get the frequencies and put a label on it. So to get the frequencies, we'll go descriptive statistics, frequencies. I will get gender, statistics. I'll just check it's in range. I always check the measurement characteristics when I first look at a variable anyway. Charts. In this case, a bar chart is going to be sufficient. We only want two groups. And raw frequencies will be sufficient to get the information I need, so we go OK. We have many more people in group 1 than group 2. From my recollection, this then is the female group, and this is the male group. Instead of calling them 1, 2, which suggests ordinality, I'm going to recode this so that all of the 2's become 0's. Okay? We'll still have people in two groups, but now we'll have 1 indicating the presence of femaleness, they're female participants, and 0 indicating the absence of femaleness, the male participants. Okay, so let's go back to the data window. Okay, we will take the sex variable, click on it there. Don't need to do the click on it, but you can see what I'm doing. Okay, the values we want here, we said we were going to have 1 female, 0 male. So this is adding the labels, but we haven't actually changed anything yet. We need to go back here and we'll go transform, recode into the same variable. Normally the best practice is to recode into different variables so that you don't corrupt your data. But since we're just making one change, it's reasonably safe to change that 2 into a 1 here, into a 0 here. So if we take gender is our old variable. Sorry, I did the wrong one. Transform, recode into the same variable. Gender is our variable here. The old and new values, we're going to take an old value of 2, change it into a new value of 0. Add that, continue, and OK. Now you can see we've got our females and males marked clearly. Right, we're ready to actually run our MANOVA now. So to run MANOVA, we go Analyze, General Linear Model, Multivariate. Okay, you can see I've already set this up previously. So I'll take everything out and just show it to you again. Okay. In the first instance, what we want here is our two dependent variables, the things being measured. So this is general measure of self-efficacy. This is our measure of academic self-efficacy. So these two things together represent two different ways of looking at self-efficacy. One the general, the other the specific. Now we're going to see if there's a difference between genders in terms of those two characteristics. Okay, we've got our gender of participant here. Alright, now we go to model. Again, we shouldn't have to change anything, but before I run an analysis I want to check that I'm actually getting what I planned on getting. So full factorial here. And it's type 3 sums of squares, which is an experimental design. This is of course quasi-experimental, but in this case the type 3 sums of squares is appropriate. And we're including the intercept in the model. Contrast, there's no point actually doing a contrast because we're only comparing two groups, male versus female. And the default contrasts here, for such as straight line fit, aren't going to provide any additional information. Alright, if we had something like age in years here, because that's got several levels to it, we want to see whether or not self-efficacy changes in a straight line way over time, we could put age in years here and do a contrast on that. But for the moment we'll just leave the gender. Plots, I think plots are always useful. Here we only have one variable to analyse, so the only place it makes sense to put it is on the horizontal axis. Post-hocs, again, we've only got two conditions. So if we've got only two conditions, there's not a great point in doing any comparison. If there's a significant effect, it's a significant effect. The post hoc won't actually be meaningful, or in fact SPSS won't allow you to conduct it. Save, we don't need to do options. Always like to go to options and make sure that we've got descriptive statistics, the estimate of effect size and the observed power turn on. They're becoming more important for statistical reporting because they help you determine whether or not the effect you got was not only significant but meaningful. Okay, estimate of effect size tells you how much variance was accounted for by the phenomena that you've observed. And observed power tells you something of the replicability of the study. Okay, this is 1 minus beta, or 1 minus the chance of type 2 error. And homogeneity test tells you whether or not you've met the assumptions required for MANOVA, so it's important to have that one turned on. We go continue and go OK. Once we've run the analysis, the first thing to do is check the specification of the design. These tables at the top of the MANOVA output tell you how many people are in each group. So here we've got 2 groups. This is male and female. We can see we've added the labels male and female. It makes it easy for us to read. We can see that there were 22 males and 116 females. Now this is an unbalanced design, so technically we've got a violation of one of the assumptions of the test and we have to treat it with caution. But before we get too excited about that, the problem here is that if you've got a grossly unbalanced design, the standard deviations, or the amount of variance in each cell, are going to be greatly different. So what we want to do to actually determine whether or not we can interpret this with any meaning, with any reliability, is look at the standard deviations and the means in each group and see if they're approximately in the same magnitude. Here we can see the means are somewhat different between males and females. That's good. We're hoping to get an effect. The standard deviation for males is 0.66. The standard deviation for females is 0.62. That doesn't look like a greatly different amount of standard deviation, and these are approximately 1/5 of the size of the mean, which is one of the rules of thumb that Sheffield presented about 100 years ago for what was an adequately shaped distribution. Okay, we can see much the same sort of values, although somewhat smaller standard deviations, for academic self-efficacy for males and females here. So it looks like any violation of assumptions is minor. The boxes test of equality of covariance matrices is non-significant, so again that gives us confidence that we can interpret the multivariate result in a reasonably robust way. We go down here and the first thing we do is say, was there an overall effect of gender on the academic self-efficacy as a whole? That's both forms together. And if we look at this, we read it just like any other conventional analysis of variance. The only problem, of course, is that the analysis of variance is given to you with 4 different flavors here. Okay, we've got Pillai's trace, Wilks lambda, Hotelling's trace, and Roy's largest root. In most cases we'd report Wilks lambda. When we've only got 2 groups to compare, Hotelling's trace is the preferable one. So here we see F with 2 and 135 degrees of freedom equals 0.673, so there's no significant effect of sex on academic self-efficacy. The p-value is equal to 0.51, and the partial eta squared, which we wouldn't, or at least I wouldn't suggest reporting because this is clearly a non-significant result, is 0.01. The observed power is very low, so this is both non-likely to reproduce and accounting for very little variance. There's little point here of continuing investigation of this data. And probably that's a good reason we should talk about looking at these figures. When you look at figures like this produced by SPSS, they tend to usually suggest that there's a significant effect simply because of the slope of the lines. But in fact, if you look at the change in scale here, this is from 4.5 as a mean to 4.65 as a mean. Let's say the maximum value for this scale is actually 5. Then this is really a very small change. So let's rescale it, which you should always do for publication or presentation purposes for assignments. We'll change the scale so it's something real. We'll put a true 0 value on there. We'll add a true maximum value of 5 on there. Apply that. We'll also make this look more like publication quality. You'll note in the caption that it talks about the estimated marginal mean. When conducting a MANOVA, the means that are used are not the grand means that you would see in the ANOVA, but rather they're a weighted composite that's produced during the calculation. They may disagree with the descriptives that you obtain by other methods, and that's why they're called marginal means. This is the academic self-efficacy. Again, I'm going to change the scale so that the minimum value is meaningful. Maximum value. Here the maximum value is in excess of 5. We want to capture that, so let's just make it 6 for the purpose of the exercise. And once again, you can see that in fact what looked like a large difference in the initial glance at the figure was actually a non-event. We don't actually need this table at the caption at the top of the figure either. We can now see the true result was that there was no effect of gender on self-efficacy. Well, there you go, a first gentle introduction to MANOVA. You can see MANOVA sounds like a complex statistic and a relatively complex test, but when you look at it, really we're only doing what you've already done with the ANOVA in the past, or with, in this case, it's effectively the equivalent of 2 t-tests. And we can see that the combined effect was that there was no effect of gender on self-efficacy, and you can see here the breakdown for each of the self-efficacies, general self-efficacy and academic self-efficacy. There's no point us talking about them because they're both, well, the overall effect was non-significant. If the main effect was significant, we would look at this table to work out where the differences lied, whether or not it was true overall or for just one of these things or both of them. And I think I'll stop it right there.